Good evening, everyone. So we started
Good
this
evening,
topic.
sir.
We started this topic. This is about probing the matter, like finding the structure of an atom, and using the particle accelerator, how we can accelerate the particle and observe their interaction. The reason why we use these particle accelerators because when we collide the particle at high speed, so we can use that energy will be converted into mass and we can use that energy to create massive particles. So that's the main reason because the in mass energy conservation will be there. Like some of the energy will be converted into mass. So we can create heavy particles using the particle accelerator. But first, how to find this experiment was there, Rutherford experiment, Rutherford gold foil experiment. What he did, he used a beam of alpha particles, which is also known as a helium nuclei, and he targeted this gold foil by the beam of alpha particle. What is the observation? He observed most of the alpha particle passes straight, few of them deviated from the path, and few of them bounced back. So if most of the alpha particles are able to pass through or penetrate through, it shows that a major portion of the atoms or major portion of the gold foil is empty. That's why most of the alpha particles are able to pass. Few of them deviated from their path. So what it shows, as we know, the nucleus, the central part of a nucleus, and the alpha particle have the identical charges. That's why like charges repel, so they deviate from their original path. And few of them bounce back. Why few of them bounce back? Because the mass is there in the nucleus, which is responsible for this reflection. So these are the observation. Most of the alpha particles uh, went straight through the foil with a little or no deflection. It shows that major portion of atom is empty. The second one is some alpha particle deflected through a large angle. What it shows the nucleus is a charge, and few alpha particle are able to came straight back towards means bounce back, which shows that the mass is concentrated at the center of the nucleus. Then to probe a matter, we can also use a electron beam. So if you are using an electron beam, we can accelerate this. The kinetic energy is equals to electrical energy. And electrical energy and the kinetic energy will be same. So electrical energy can be used like electrodes can be used to accelerate this electron to a higher speed. So kinetic energy is half mv square and electrical energy is voltage into charge. So using this, we can find the speed at which the electron will move through the region. And if you want to remove the electron from the substance, there's a photoelectric effect. In AS, we discussed this in detail. When light of certain frequency falls on the metal, if the energy of the photon is greater than or equal to the minimum possible energy, which is also known as a Warp function, then there will be a photoelectric effect. Or thermionic emission can also be done. Like when we supply heat energy, the metal tend to lose electron from its surface. We call that as thermionic emission. So both ways we can release electron, and then we can use electric field to accelerate the electrons. And we can use this beam of electron to investigate the matter. So how we can use the beam of electron to investigate the matter? So if we want to find or investigate the structure of the crystal, so we can use X-ray diffraction or we can use electron diffraction. In X-ray in X-ray diffraction, what will happen? X-rays are electromagnetic radiation. So when the wave passes, these are the wave front, not the wave. So when the wave passes through the crystal, diffraction pattern are observed. So what it shows that the wavelength is comparable with the spacing, the distance between the ions. so diffraction occur. When we carry out the similar experiment with electron beam, so what we observe, we can change the speed of the electron by using a different electric field. So when we use an electron, a beam of electrons, so what we observe most, if it electron is a particle, then it should pass straight, or it should deviate from the path, or it should bounce back. But we don't observe this pattern. What we observe when we are using electron, we observe a similar diffraction pattern, which we observe with X-ray. So what it shows electron is not acting like a particle, it is acting like a wave. And the wavelength associated with this electron matches with the gap size. So that's why diffraction occurs. And how we can find this wavelength? We have the formula lambda is equals to h over p, which relate the momentum, and p is a momentum, lambda is a wavelength, h is a Planck constant. So this relation, de Broglie's wavelength, which shows the wave particle duality, means the particle can behave like a wave. So in an electron probe, what we do, a beam of electron is fired as a crystal, and we can change the momentum. How we can change the momentum? Momentum is a product of mass and velocity. If non-relativistic effects, the mass will not change. But as we increase the speed, accelerate electron, so the wavelength associated with the electron will get shorter. So we can get more detailed image of the lattice. So a beam of electron is fired as a crystal and shows the diffraction pattern. And this confirms that the wave particle duality means the particle can behave like a wave, or wave can be a particle. So if we want to get a more detailed image, like more diffraction, so we should increase the momentum. How we can increase the momentum? By using a higher momentum is a product of mass and velocity. Mass is constant, velocity we can change. And how we can change the velocity? We know kinetic energy is equals to voltage into charge. So if we apply a greater voltage, mass and will not change. So speed of electron will change. As the speed change, the momentum will change. Increase in momentum will lower the wavelength. So we can have more detailed image of the lattice. For linear particle accelerators, we use accelerator to study the interaction of the particle. So why we need accelerator? Because we want to produce more fractions, more particles. So to create more particle, energy can convert into mass. So if particle is accelerated to high speed, and when we observe its collision, we can use like form new particles. So how a linear particle accelerator or a LINAC work? So it consists of a cylindrical tube, and each tube is different in size. We apply an alternating voltage. So if, for example, if there's a beam of electron, so first positive, negative, electron is accelerated. Once electron reach the plate, the one end, the terminal changes. But this change in terminal does not affect the electron. It will move with a constant speed in this region. Why? Because there is no net electric field inside. But the moment it will come out from the tube, again the terminal change. So this will become positive, negative. So electron is accelerated. Between the plate, it is accelerated, and every plate it is taking the same time. Means the time taken by electron, if it was 0.1 second in plate A, it will be 0.1 second. That's why it should take the same time, so that every time it will receive the same potential voltage. Otherwise, if the time interval is different, it will not receive the same voltage. So as we know, speed is equals to distance over time. So it is taking the same time. So time is equals to distance divided by speed. So what happened? The distance between the distance traveled by the electron increases within the cylindrical tube, but its speed is also increased. Like every section, it is accelerated. This part, it is accelerated before entering tube B, accelerated before entering tube C, accelerated before entering tube D. It was also So distance increase, the length through which electron is passing increase, the velocity is also increased, but the ratio remains same. So it will take the same time to pass through each tube. And we can have interaction of electron with any other stationary object, or it can be a moving object, but in opposite direction, moving particle, and it release energy as well as produce different particles of different mass. Then, as we know, if we have a charged particle, whenever the particles are charged, these charged particle experience, because whenever there's a charged particle, moving charged particle, it produces magnetic field. So this magnetic field interact with the magnetic field of a permanent magnet. So cross means the magnetic field is into. If you want to find the force on the charged particle, so you will use Fleming's left hand rule. So Fleming's left hand rule can be used to find. So first finger in this Fleming's left hand rule, the first finger represents magnetic field, which is pointing into. The second finger represent direction of the particle, and the thumb will represent the force which the particle experience. So in this case, the first finger, as you apply the rule, the first finger should point into, second represent direction in which the particle is moving. So you can see clearly the thumb is pointing up here, so the direction of force is up. So this direction of the force cause the rotation, or object will move in a circular path. So it's easy to just apply the rule, because sometimes you don't have know the particle. So you can apply the left hand rule. If it follow the left hand rule, it means it is a positive particle. If it does not follow the left hand rule, it means it is a negative particle. Then how we can find the force on the charged particle in a magnetic field? So the formula, because when an object is moving in a circular path, the formula is mv square over r. And when there is a magnetic field on the charged particle moving through a magnetic field, the force experienced by charged particle is equals to bqv. B is the strength of a magnetic field, q is the value of the charge, and v is the speed at which the particle is moving. So if we compare the two equations, this v will cancel with the square. So r is equals to mv over bq, or mv is the momentum, so r is equals to p divided by bq. So this formula can be used to understand the particle momentums as well, using the curvature. Like you can see, this is a small curvature. Another particle, this is a large curve, means greater radius. So when we compare the momentum of A with momentum of B, so as B is having a large radii, so means it will have a greater momentum. So you can using these, the curvature of the curve path, or curvature of the path, you can identify the momentum as well for particles moving in a magnetic field. So greater curvature means higher value of R, it means greater momentum of the particle. So radius increases with the increase of momentum. As you can see, this formula, it shows momentum and radius are directly proportional to each other. Another type of particle accelerator is known as cyclotron. So what we do in a cyclotron, we use both electric field and magnetic field. In linear particle accelerator or LINAC, we only use electric field to accelerate. And this linear particle accelerator should be several kilometers long to accelerate the particle to kilovolts. But for cyclotron, the advantage of cyclotron, because we use a magnetic field, so this particle can cover a greater distance in a circular path. Eventually it will reach out and have a collision. So example, if we want to accelerate proton, so we have a source of proton. These are known as the Ds, and outside we apply electric alternating current is there. So first what happen, example, if the particle is coming out, so one of the D will be positive and the other D will be negative. So electron accelerated, the proton accelerated. It can be, the first one is because for acceleration it should be opposite pole. So if there's a proton, so negative terminal and then positive terminal. So what happened? Proton accelerated, but within the D there is no there is acceleration because of direction, but there is no change in speed because electric field is responsible for change in speed. But what happened, because there is a magnetic field between the D's? So if this was a top view, and this is a D. So when, say, proton accelerated, then deviate. Within the D, it is only changing the direction, accelerating because there is a change in direction, but there is no change in speed. Why there is no change in speed? Because there is no electric field within the D. But moment it will arise, so it will accelerate, and then again it will deviate. Again it will accelerate and deviate. Why the radius of the curve path is continuously changing? Because its momentum is changing. And how the momentum change? Because we are using electric field, so velocity change, so momentum will also change. That's why the radius, even though there's a constant magnetic field, but the radius is changing, and eventually we can have a collision at any point. So cyclotron is consisting of the two Ds, which are connected to this high frequency AC supply. The particle accelerated in the electric field between the two Ds, and the polarity of a D changes for every half cycle, so it will continue to accelerate. Purpose of the electric field is to accelerate. Purpose of the magnetic field is to deflect. Is it clear? Is it clear? The cyclotron? Okay. So you can see this is a passage, the path which the particle will, so it is accelerated, then deviated, then accelerated, then deviated, accelerate, deviate, and eventually it will reach out and collide with other. This is an exam style question. So typical student answer is there. The diagram below represent a cyclotron that is used to accelerate the proton. The proton enter the accelerator at the center and spiral out. So why do the proton accelerated, moving from one half to of the cyclotron to the opposite half? So what is the reason for the acceleration? The reason for acceleration, because the opposite D's are there, opposite potentials are there. That's why it is accelerated. The largest radii of a circular path that a proton can follow is equals to radius of a cyclotron. Means that's a complete path which it takes. Shows that the maximum speed of a proton is equal to BQR divided by M. And so how we can represent? Because when it is moving in a cyclotron, the centripetal force, because it's moving in a circular path, so centripetal force, and centripetal force is due to the magnetic force, and centripetal force is given by mv square over r, and magnetic force is bqv. We can solve this and find the speed. Then calculate the maximum speed of a cyclotron. The magnetic field strength is 0.6 Tesla. Q is the charge of a proton, 1.6 exponent minus 19. R because the radius is there of this cyclotron, which is about 0 0.8 meter, they already mentioned, divided by mass. Mass of electron is mass of proton is 1.67 exponent minus 27 kilograms. So you substitute and you will get 4.5 exponent. But if you check norm, as they mention here in this, the diameter. So if a student substituted instead of radius a diameter, it will be 4.5 exponent 7, and it is very high speed. When it moves closer to the speed of the light, then relativistic effect, the mass does not remain constant. That is why r should not be 0 0.8, it should be 0 0.4. Then state difference in the path followed by a charged particle being accelerated by synchrotron compared to that cyclotron. So synchrotron is using a variable magnetic field. Basically what happened, because if in a cyclotron we use a constant magnetic field, and that magnetic field is only able to change the direction, but because the speeds are different, that's why it is having a spiral path. But in synchrotron, what we have variable magnetic field. Magnetic field is not constant. As the speed changes, we change the strength of a magnetic field so that it will remain in its path, circular path. So the radius of a circular path that the particle follow is kept constant. And how it is kept constant? The particle travel in a vacuated chamber, and that is having a shape of a ring. So we use different magnetic field, like the strength of the magnetic field in cyclotron is constant, but in synchrotron it is not constant. It is continuously changing variable magnetic field, which cause the path to be same. Otherwise, if it was a constant, because the constant magnetic field, as the speed is continuously changing, so it will have a spiral path. Then the particle detectors, basically after accelerating the particle, we carry out the the one particle collide with another one, and then we detect these particles. So for particle detectors, what we can do, different particle detectors can be used. We can use a Wilson cloud chamber, or we can use bubble chamber. You don't have to learn the detail of how these chambers are working, but the basic idea is that because they contain particle, like one is uses a supercooled vapor, another one is superheated hydrogen. So both cases, what it cause, when the particle enter a region, the charged particle, not a neutral, so these charged particle cause ionization. Ionization means they knock out the electron. So when they knock out the electron, these radiation, this cause energy to emit out, and we can trace this energy which is emitted out, and we can sketch a path through which the particle is moving. So this is a cloud chamber. The working you don't have to learn. Basically what happened, source of the particle, and so when the radiation enter, these radiation cause ionization, energy is emitted out, and using this energy we can trace the path of the particle. So example, you have paths are shown. First saying, explain the principle of cloud chamber for detecting the particle. What is the basic principle? The cloud chamber, basically, the vapors are there. When it become ionized, they lose energy. So a cloud chamber contain a pad of a soap and ethanol, which vaporize when the pressure is reduced, and incoming ionizing particles ionize the air in the chamber, and ethanol on a trail of ions, making the path visible. So basically, why the path is visible? Because the particles are causing ionization. If it's a strong ionization, then it will be a continuous and a broad path. If it is weak ionization, then discontinuous paths will be there, or thin line. The track were obtained from for particle moving in a magnetic field at a right angle to the plane, as shown. Explain what can be deduced about what is happening at a place A and B. So at A, what is happening? At point a neutral particle at A, the particle has decayed into two particles and one is uncharged. And at B, an uncharged particle has decayed into two oppositely charged. So what we can say, because look, the particle was moving in this direction and it deviate from the path. So because there was an initial path, if there is an initial path, so it shows that originally it was a charged particle. But because the momentum should be conserved, so if it changes the direction, so there should be another particle, because the initial momentum should be equal to the final momentum. So if this was the original path and it deviated from its path, so but there is no other particle we see, but there should be other particle. Why there should be other particle? Because to conserve the momentum. If initial, what is the initial momentum? The final, because if only the direction changes here, means the momentum is not conserved. The momentum before and momentum after is not same, because the direction you can see are. So there should be another particle to conserve the momentum, but that particle path is not visible. So what it shows? It shows that there will be uncharged particle. What about B? For B, we did not see the original track, and suddenly we see two particles are in opposite direction. So if two particles are in opposite direction, so what just gives an idea? This shows that B decayed into oppositely charged particle, and which are having momentums. Now you can see what difference there would be. A track of electron and the proton in the same magnetic field. So what will be the difference in a track for first one? So the proton track would be curved in opposite direction and would be thicker and shorter, because they have more mass, but because they're moving at a slower, they have higher momentum. Moving at a slower can have a short range. That's why the length of a track will be shorter. Is it clear? The track in a cloud chamber, or it can be a bubble chamber. And you can see some of the tracks. Example, if the magnetic field is into. So first finger represent magnetic field, second represent direction of the particle, thumb is pointing up. So positive particle will go up, negative will move down. So this will be the track for fast moving particle. So fast particle make a thin curved path. Now what happens as the particle is losing its energy? It will have a spiral path. Why spiral? Because it's continuously losing its energy. So speed is decreasing. As the speed decreases, the momentum will also decrease. So radius will decrease. So particle lose the kinetic energy through ionization. So the track is getting more curved and less thicker. The radius is decreasing basically. And why it is getting? Because the particle is continuously losing its energy at a greater rate. That's why the track is getting thicker. If slow and a massive particle, so this will give more ionization, so thicker track will be there. And a decay into a charged particle and a massive particle, which itself decay into oppositely charged. So you can see. So basically what happened, this track, first a particle was moving at a high speed, it decay. This decay produced two particles, one neutral particle, another one charged particle. But because why the path is not a curve here, even though there is a magnetic field, it shows that it is having a very high momentum. That's why the path is not curved. And then this neutral particle further decay into particle n, like positive and negative particle, which are having a different momentum. Why? Because you can see their curves, the radius is not same. So similar, what A is representing, electron and positron curve in opposite direction. So that's for A. B is electron loses energy through radiation, like an inward. So electron was moving, it is losing energy, so radius is decreasing. C is the particle coming to rest, leave a dense track near the end as it ionize power, as its ionizing power increases. The dense track here refers to greater ionization. For D, because originally there is no path and then it deviate into two, so it shows a neutral particle which cannot be seen, because we cannot see neutral particle, only charged particle can be seen. And but it gives two tracks in opposite direction. So what it gives an idea, two charged particles are there which are traveling in a straight line in absence of magnetic field, or or if there's a magnetic field it will be a curve, but if even there's a magnetic field and the particles, the path is not curved, so it shows that they are having a high momentum. And the charged particles emitted a neutral particle which cannot be seen, but the thing is there should be a neutral particle so that there will be a conservation of the momentum. This is a typical exam style question. A high energy gamma photon enter a bubble chamber and produce electron and positron. So electron and positron, but photon is a neutral. That's why you don't see the track of photon. But at this point, the photon decay, and it decay into two particle, electron, positron, and electron. Then we have to explain the magnetic field is into. So if the magnetic field is into, you have to identify which is proton and which is positron and electron. So your first finger should point in. The second represent direction of the particle. So thumb is pointing up. So if when I apply the rule, Fleming's left hand rule, my first finger should, they already mentioned magnetic field is into. So my first finger should point into, second represent direction of the particle, and direction of the part, because it cannot be other way around, like it cannot have direction, as the momentum is not increasing, energy is decreasing, speed is decreasing due to ionization. So it will always be in opposite. So first finger represent magnetic field, second represent direction of the particle, and thumb is pointing towards center. So when I apply a left hand rule for path B, it follow left hand rule. So it means the path B is due to the positive particle, or which is positron here. So opposite, if I apply a rule, first finger represent magnetic field, second represent direction, but it is not following the left hand rule. So it means this is a negative particle. So the particles are moving in a circular path due to magnetic field, and direction of the magnetic field is perpendicular to direction of the motion. The two particles are oppositely charged because their curvatures are different, opposite direction. The particles spiral in opposite direction. That's a reason. Then using a Fleming's left hand rule, B follow the Fleming left hand rule. So B is positively charged, and it is a positron, and A is electron. Then the fact is, the both tracks have the same curvature or radius, so shows that both have the same mass to charge, or we can also say both have same momentums. Is it clear, this one? Because you will find a question in which you have to explain the path why the particles took that specific path. Another picture which shows the movement of the particle. So the question is, at x, an incoming charge particle, at this point x, incoming charge particle interact with a stationary proton. So this is a charge particle is coming and it interact with a stationary proton and produce a neutral lambda particle, a neutral kaon particle. Both of these particles later decay into other. With the reference to photograph, describe and explain the evidence for or this event. Like how this photograph is an evidence that this happened. So why? Because after x you don't see the path. So if you don't see the path, so it means there are neutral particles are there. And neutral particle they went on and later we see the path. So why we see the path? So it shows that the neutral particle decayed. These neutral particles they went on and seen track in V shape, decay into two charged particle and to conserve the charge, and newly formed charged particle move in different angle to conserve the momentum. So this was about the particle physics, particle accelerator. We are done with particle physics. The last topic is left, which is about magnetic field, and we'll discuss that on Thursday. So we'll complete unit 4 on Thursday. Any doubt related to the class? Okay, so I'll end the session and share the recording.